Good morning, everyone. Good afternoon for people attending from a different time zone. It's my pleasure. It's quite amazing to see the BTR attracting a significant number of participants over the years. This is the fourth BTR, and very proud of this conference, happening and continuing every year. So today we have a session packed of very great ideas and research. We have in total 6 presentations covering all aspects of public transportation and planning. Some of them related to the COVID pandemic, some of them related to resilience and electrification as well. We have 2 presentations which will be played off videos and 4 live presentations. So we will try to limit the presentation time for 15 minutes and then followed by 5 minutes Q&A. We already starting 2 minutes behind, so we will try to make it 4 minutes for Q&A session for each presenter. So our first presentation is led by Ahmed Foda and co-authored by Ali and Moataz Mohamed. And this is mainly about optimal or not optimal, the impact of optimization approaches on battery electric bus system configuration in transit application. Ahmed Foda is a PhD student at the TRIP Lab at McMaster University, working under my supervision, and his research mainly focuses on the utilization of advanced optimization techniques and models in electric bus transit network configuration. So without further delay, if we can play Ahmed's recorded video. I know Ahmed is currently on vacation, and he's attending to answer questions. If he's not available, I will actually answer question on his behalf.
Hello everyone, my name is Ahmed Foda, PhD student in Civil Engineering at McMaster University. Today I will present my work titled by Optimal or Not Optimal, the impact of optimization approaches on battery electric bus system configuration in transit. I will present on behalf of the authors of this paper, me, Ali Saleh, and Professor Moataz Mohamed.
Before I start the presentation, I would like to acknowledge the contributions of my colleagues at the Transit Research Informal Practice Lab, and also the support from the Nature Sciences and Engineering Research Council of Canada. This presentation is outlined in 6 sections. First, introduction and motivations. Second, research gap. And third, the proposed model, which is the charging infrastructure and the schedule model for battery electric bus system. After that, I will explain the case study, fifth results, and at the end, the conclusion. Today is one of the main challenges facing our planet is the global warming problem, which is related to the greenhouse gas emissions. The transportation sector represents a major share of global greenhouse gas emissions. For example, 29% in US and 25% in Canada. In addition, the population growth in many countries will bring about increased demand for public and freight transportation services, which will increase the transportation-related greenhouse gas emissions. In order to reduce the global greenhouse gas emissions, Canada has joined other countries to commit to net zero emissions by 2050. And for a short-term target, Canada commits to cut its greenhouse gas emissions by 40 to 45% below 2005 levels by 2030. Motivated by the high share of the transportation sector greenhouse gas emissions, it is often flagged as the first target for emission reduction. The question now is how to reduce the transportation-related greenhouse gas emissions. The answer is in the electrification. Which sector or which field will be electrified? Recent study highlighted that electrifying the public transit network by using battery electric bus could bring significant per passenger greenhouse gas emissions. The amount of greenhouse gas emissions reduction if we use battery electric buses in public transit network is related to the electricity sources. If we use renewable-based electricity, it will be almost net zero emission network, and if we use different types of electricity sources, the reduction will be around 41%. The other feature which make the public transit network as a potential target for full electrification is the public transit network characteristics like fixed routes, fixed schedules, and shared infrastructure, which make the transition toward electrification smooth. The main drawback of using battery electric buses in public transit network is the operation range. Therefore, we can say that battery electric bus system configuration required a sophisticated planning, design, and optimization efforts before moving out fossil-fueled buses. The previous studies of battery electric bus system configuration can be classified in three categories. The majority of the previous studies aimed to reduce the upfront costs of the battery electric bus system. Therefore, this studies is cost-based optimization models. Few studies aimed to reduce the impact on the utility grid network. As we know that battery electric buses using high power chargers to charge the buses. Therefore, this study is focusing on reducing the impact of these chargers on the utility grid network. The other few studies taking the main aim of using battery electric bus system in public transit network, which is reducing the greenhouse gas emissions. The gap is that all these studies taking one approach in optimizing the battery electric bus system configuration, but there is no previous study investigate what is the impact of changing the optimization approach using the same model. After choosing the objective functions, the previous studies vary significantly in classifying which battery electric bus system components will be optimized and which will be taken as a predefined value. All the battery electric bus system components like chargers, power of chargers, battery capacity should be taken as a decision variables to achieve the trade-off between them. After choosing the system components which will be optimized, the previous studies varies two categories in choosing the charging strategy. There is two charging strategies: en route charging and overnight charging. Overnight charging requires a sizable battery capacity. Recent study ensures that choosing en route opportunity charging, which is partial and continuous charging, will optimize the utilization of resources. In this work, we have two main research questions. The first one is, will the battery electric bus system configuration or the component sizing will differ according to the study approach or the optimization model objective function? If we target reducing the upfront costs or mitigating utility grid impact or reducing the greenhouse gas emissions, will the system configuration differ from one approach to another? The second question is, what is the added benefit of using energy storage system as an alternative electricity source in the charging station to charge the battery electric buses in the three different optimization approaches also? In the proposed charging infrastructure and the schedule model, all the battery electric bus system components are taken as decision variables. For the charging station configuration, number of chargers, power of chargers, energy storage system capacity, and energy storage charger power are taken as decision variables. For the fleet configuration, we maintain the previous well-established network timetable. Therefore, the number of buses in the battery electric bus network will be equal to the number of buses in the fossil-fueled network. Therefore, we only optimize the battery capacity. The proposed model produces the optimal charging schedule, which is en route, partial, and continuous charging schedule. Therefore, the schedule will contain for every charging event the starting time, end time, and show the charging duration. For the objective functions, we solve three different models. The first one is cost-based optimization, which include the infrastructure and the maintenance cost, like construction, chargers, energy storage system, and the battery electric buses costs. The other model aims to reduce the operational cost, which is the electricity cost related to the time of use tariffs. The third model, reducing the greenhouse gas emissions, which in our case is the well-to-tank greenhouse gas emissions based on the temporal distribution of the electricity sources. The three different objective functions of the proposed model are as follows. First, minimizing infrastructure cost, MIC. The infrastructure cost is like the cost of chargers, the cost of the battery, cost of buses. The second one is minimizing the operational cost, MEC, and the third one is minimizing the greenhouse gas emission cost, MGEC. All these three different models are solved under the same constraints. I omit the equations of these constraints because it's like 40 equations, but they could be summarized in the following points. The constraints consider first the well-established network timetable to maintain the level of service. Second, the operational constraints. Third, an accurate trip-level energy consumption model. Fourth, in-route partial and continuous charging strategy. Fifth, the electricity time of use tariffs. And last, the well-to-tank greenhouse gas emissions temporal distribution. The three proposed models are applied in a real-world transit network in Basel City, Ontario, Canada. For the first model, which is minimizing the infrastructure cost, we have 170 charging events during operation. All these events are directly from the utility grid because of the high cost of the energy storage system cost. The system components is 6 chargers with rated power 400 kilowatt, and the battery electric bus battery capacity is 100 kilowatt hour, and the annual greenhouse gas emissions is around 75 ton CO2 equivalent. For the second model, which is minimizing the electricity cost, we have 101 charging events during operations. 75 are from the energy storage system, and 26 are directly from the utility grid. All the 26 events are on the off-peak period. The system components are 7 chargers with rated power 300 kilowatt, and the battery electric bus battery capacity is 350 kilowatt hours. The energy storage system energy to support the 75 charging events is around 1,600 kilowatt hour, and the energy storage charger rated power is 150. The well-to-wheel emissions is around 41 ton CO2 equivalent, which is less than in the previous model because of the correlation between the off-peak period and the hours of low greenhouse gas emissions. The third model, which is minimizing greenhouse gas emissions, we have 80 charging events. All of them are from the energy storage system because the working or the operating hours have a high greenhouse gas emissions. Therefore, all the charging events are from the energy storage system, not from the utility grid. The system components are 3 chargers with 300 rated power. Battery electric bus battery capacity is 400 kilowatt hour. Energy storage energy is around 1,700 kilowatt hour, and finally the energy storage charger rated power is 160 kilowatt. The annual greenhouse gas emissions is around 38 ton CO2 equivalent. For the answer of the two main research questions of this work, for the first question, the answer is yes. The system components are different from one approach to another. As we see here, the number of chargers varies from 3 to 7 in these approaches, and also the energy storage charger rated power, energy storage energy, battery electric bus battery capacity, and the charger rated power is vary significantly from one approach to another approach in the optimization model. For the second main question, which is what is the added benefits of the energy storage system in the cost, utility impact, and environmental aspects. For the cost, there is no energy storage system is utilized. For electricity and greenhouse gas emissions, the energy storage system is used to reduce the electricity cost and greenhouse gas emissions on the on and mid-peak periods. To summarize this work, we can say that this study has developed 3 novel optimization models for the battery electric bus system configuration in transit operation, minimizing infrastructure cost, minimizing operational cost, and also minimizing greenhouse gas emissions cost models. These models consider operational constraints, the well-established network timetable to maintain the level of service, electricity time of use tariffs, the temporal distribution of well-to-tank greenhouse gas emissions to optimize the utilization of resources, partial and continuous charging strategy, and also an accurate trip-level energy consumption model. All these models are applied to a real-world transit network in Belleville City, Ontario, Canada. The take-home message from this work is as follows. First, the resultant battery electric bus system configuration varies significantly according to the objective function. Secondly, the results of this work ensures that the battery electric bus system configuration necessitates the inclusion of multiple objectives. Therefore, successful battery electric bus system configuration should consider infrastructure and operational costs, utility grid impact, and also the well-to-tank greenhouse gas emissions in one model. Therefore, we recommend utilizing a multi-objective optimization problem for battery electric bus system configuration because the Pareto optimal front produced by the multi-objective optimization will illustrate the trade-off between these conflicting objective functions and will enable the decision maker to select the best compromise solution. Thank you so much for your listening, and I will be more than happy to answer your questions.
Okay, thank you, Ahmed. I noticed that we have Ahmed in the meeting and Ali as well. So let's say we have 3 minutes for Q&A session. So if you'd like to use raise hand function or type your question in the chat, I'm more than happy to read it for you. You can just unmute and fire up.
How many minutes does he have before the next presenter, Moataz?
We have maximum 3 minutes for the Q&A session. So since you turned on your camera, Cora, so go ahead.
Oh, I didn't come up with any questions. You know, I have a battery electric bus paper or 2 with Moataz. So yeah, but I was being asked yesterday questions about battery electric buses and who the transit agencies in the US turn to with questions like this. What should we purchase and how should we use it? So I don't think your student knows the answer to that question. I'm not sure anybody here does, but please feel free to put an answer in the chat box if you have any guesses on a good point of contact for that technologist.
Okay. I will shoot you an email.
What'd you say?
I will send you an email about like the market share of several manufacturers in the US.
Yeah, well, I think we know manufacturers, but like a group of agencies, like who would they go to as a consultant, maybe? Not an equipment sales, but a consultant.
Okay. So perfect. So just for everyone in the meeting, I think recently Metrolinx, which is the Crown Corporation and managing the GTHA, Greater Toronto Hamilton region, in terms of transit, they created like a group acquisition for feasibility analysis for electric buses in Canada. And this contract was awarded to HDR Consultant in the States. So HDR will be responsible in doing feasibility analysis for 13 different transit networks in Canada. If you want, let's say, a technical perspective or a network level feasibility, you can always refer me. I'm more than happy to do this for like under research partnership or consultation fees, whatever. But like I can say the focus shouldn't be on a route level feasibility. This is quite frustrating for me to see that most of municipalities are looking into route level feasibility. When you optimize a route, it's a completely different story from optimizing the entire network. Sometimes you allocate more resources on a given route because the impact on the entire network will be optimal. So if any transit agency is considering electric buses, they should study the feasibility at the network level and then study the implementation at the route level. However, feasibility shouldn't be explicitly done on a route level because the results will be extremely biased and will be misleading.
Thank you.
Okay, perfect. So I think we can start the second presentation. So until we share the screen, second presentation by Tamara is informal transport flexible. So Tamara is a PhD student at the Department of City and Regional Planning at the University of California, Berkeley. She worked on significant number of projects related to the World Bank, NGOs, public sector in Israel, Palestine, Djibouti, Burundi, and Democratic Republic of Congo. So a lot of developing country, which is great to see transportation studies over there. And Tamara's research focused mainly on a comparative study of transport planning in the informal sector of Malawi, Uganda, and Kenya. So as a proud African with Egyptian background, I welcome Tamara, and the floor is yours. Whenever you see my video on, it means that you have 2 minutes left of your presentation time.
Hello. So I'll just get into it. My research looks at the way transportation networks operate, primarily in major East African cities at the moment. So what's often called informal transport or paratransit is really the most important mode of motorized public transportation across a large part of the world. And many of us will be familiar with these small vehicles. They're called different things in different places, marshrutkas in the former Soviet Union, trotros or matatus or minibus taxis across Africa, colectivos in some Spanish-speaking countries, jitneys, et cetera, et cetera. They have very different operating models and very different ways of existing in different cities, but there's a few commonalities we can point to. These are mostly smaller vehicles. They're often independently owned. So it's not a large firm and certainly not the public sector, and often highly atomized, which is to say, even if a given person or entity owns multiple vehicles, they will lease them each out as a separate business, and they don't really pool their resources in any way. So maybe picking up a little bit this question of optimizing, thinking about networks from the given route or stop or location or vehicle in this case to actually how the network operates in the big picture. And then the person that it is leased to, usually the driver, is responsible for paying this lease every day in a very informal way. So there's really limited ability to kind of build up capacity and build up resources over time. And on the other hand, it's a really easy business to get into because usually governments, even if they have a degree of regulation, they have very little protection on entry. So if somebody wants to add another vehicle to a given route, nobody's checking like, does this route need it? Right? We may have too many vehicles in one place, too few vehicles in another. So my main question, what my dissertation focuses on, is sort of this last bit on how do these new routes get formed and decided on, and how are vehicles allocated across space in this kind of network without a central planner. So this is some work from Djibouti, for example. We can map out these routes and we see they have like a certain constancy and stability, but we don't really understand why a given network looks the way it does, why these roads and not other roads, why these constellations of routes and not some other one. And the question is, so who makes these decisions and who holds that power, and what is their logic in pulling this together? So one of the key actors is the drivers, who work on what's called this target system, where they're paying the lease every day to the vehicle owner. And they only get to keep what they make over the lease. The lease is usually set pretty high. So even if they've had a really bad day, even if the vehicle's broken down, they've been stopped by police, which happens very frequently, there's been terrible traffic, there's been flooding, whatever. They may get absolutely nothing. The contract requires the owner to still get the payment. So they're really carrying all the risk of the operation. And they work very long hours. The incomes can be really unpredictable. The studies that we have across Africa and Latin America show really, really long working days, up to 14 hours. And it's a tough job. It's physically painful. It's many, many hours spent in this vehicle. It's really, really stressful. It's this constant negotiation of quite chaotic roads and of often angry and annoyed passengers. It's just not an easy job to have. So the idea is they're the ones making most of these decisions because the owner of the vehicle is not really involved. And at the same time, government and state regulators tend to have a pretty hands-off approach. So the existing literature kind of suggests a very laissez-faire, kind of invisible hand market logic, right? There's multiple vehicles, multiple drivers, they're all competing to pick up as many passengers as they can. And that means there will be a sort of fine-grained diversity of service. A lot of the literature uses these ideas of reactivity and response to demand and flexibility, in which each of these independent actors are able to kind of intuitively almost understand segments of market demand and respond to them, thus creating what is in some ways argued to be a really well-adapted network to sort of passenger needs. There's also a social side to this, sort of a different strain in the literature argues that these local ties and social connections are every bit as important as the simple market logic. But in terms of planning, to me as a planner asking, okay, so where does this mean about stop and route locations? These two arguments kind of seem mutually supportive. They just offer slightly different threads of the same mechanism of flexibility and response to demand. However, I find doing quite a bit of field work and actually going out, talking to passengers, talking to bus drivers, that there are big gaps in the system. This idea that these mechanisms are able to provide the services that people need, I think, and what we've been finding increasingly empirically is just not the case. When you go and interview people, both quantitatively and qualitatively, when we survey mobility patterns and we ask people how they're using the system, we see huge gaps. This interview from Lilongwe, I can't visit my friends. People are saying it's too expensive and it's too far away and I don't have the services I need to get there. We asked people in Djibouti what activities they wanted to go do but could not. And it's everything from visiting my sick parents to going to see the football game, right? So there's really basic daily functions that are not being served by these transport systems. If we look at this in a more quantitative way, this is some work we did with the World Bank a few years back, where we tried to map out job locations and run an accessibility analysis using mapping of these informal systems. We see that there's some locations that get decent enough service, but huge areas across several cities that are really, really almost cut off from much of the urban core. And if we just overlay this on population density, those are not sort of peripheral locations. These are areas with high density populations, high density of population. And at the same time, some cities are doing better than others. So Lusaka in Zambia has seemingly a much stronger pattern of accessibility than, say, Dar es Salaam or Cape Town. And my research really is trying to understand why in some cases these networks are operating in a more efficient and more effective manner for more of the population across different cities. So the idea is, I think it sort of boils down to a notion that there's a trade-off in this sector between more regulation and more flexibility, right? There's all these substantial negative externalities to this kind of free atomized operation, which is really poor safety, a lot of speeding, right? These vehicles are constantly competing with each other to pick up more passengers. So there's this like aggressive, fast driving, which leads to a huge amount of accidents. These vehicles are severely undercapitalized. They're often in very bad condition. Nobody has any particular interest in kind of extending their lives or doing good maintenance on them. So there's a lot of pollution, and then that exploitative and difficult labor relationship, as well as the gaps for passengers. So in many, many cities, there's also a layer of self-regulation. So there are cartels or firms, associations, unions, and across East Africa, SACCOs, which is saving and credit cooperative organizations, are also quite common. And they offer a level of control that's sort of beneath government, but often very effective in regulating the way these small vehicles operate collectively. So even though they're still all independent, you need to pay a fee to join a particular route. You need to, there is a mechanism for queuing, which makes it fairer. So people aren't just, vehicles aren't just sort of wildly competing. Everybody sort of is expected to take their turn. And then in a few places, they actually also select where new routes and new terminals are going to be. So there's this idea that there's a trade-off here, though, because these organizations are coming in and they're limiting the flexibility of the system. That means maybe it's a little bit safer, it's a little bit better organized, but that ability to respond to passenger needs is weakened. And I think we just don't see that trade-off in practice. So just to get to the empirics of this a little bit, this particular piece of this research is based on research in 5 cities, which was completely opportunistic. These are just cities where I've worked and where I have opportunities to collect data. And what's the interesting opportunity that was presented here was that there's sort of 2 typologies of the cities here. So 3 of them, Lilongwe, Djibouti, and Lubumbashi, have what's the sort of classical atomized invisible hand type system, where there's really the association level organizing is very, very weak. There's a few of them, but they're not doing a lot of the like much heavier work that we see in a place like Nairobi, East Jerusalem. I've also been working in Kampala for the past year. There it's even stronger. So these major metropolitan areas where there's long, long histories of these in the informal system, and a lot of management and a lot of capacity within this informal regulatory internal structure. Whereas in other cities, particularly a place like Lubumbashi or Lilongwe, which have really grown very, very fast in the past decades from very small towns and don't have that like long urban history that a place like Nairobi or Jerusalem or Kampala does, those associations are still much weaker. They haven't built up that capacity. And then, so what I've been finding, interestingly, is, first of all, looking at those less organized cities, there is a lot of freedom for drivers compared to the more organized cities. They are able to choose new routes. They're able to drive to any destination that they want. They can pick a new location. They can drive off route. They operate on multiple routes per day and switch between them pretty freely. But at the same time, they're not doing that kind of exploratory attention to demand, follow the passenger's needs behavior. We asked them if they could, and they're like, yes, we could. And we just don't. This is not a thing that we can do. And the reason is, as far as I can tell, because it's just not sort of safe. They actually have to have very, very conservative operating behavior. And if you can see the map of Lubumbashi here, where we charted passenger volumes, this goes back to a big project in 2015. There's a lot of concentration, despite the size of the city and despite how much it's sprawling around this network, where so much of the passenger services, of the vehicles, are concentrated on these central corridors because they know they're going to meet their target. If we go back to that target system, they know on these corridors, there's enough passengers to generate the amount of money they have to pay for the vehicle that day. Because if they miss this payment more than a few times, they just lose the job. So that ability to kind of take a risk and say, okay, I'm going to start a new service. I'm going to test a new possibility. I'm going to like go to a new destination. That's really, really risky behavior that they have no resources to do, because they have to meet their target day by day by day. There's no savings here. There's no ability to invest. We can also see that on the map of Lilongwe, which is a little bit more recent, where there's a few routes missing from this. We found them thanks to another project later, but not many. And there's still huge built up areas that are really receiving no service at all, despite demand, despite a need there. So then the comparison, to kind of nail this down, looking at Nairobi, which is again much more organized and where government regulation requires that every vehicle belong to an association of a minimum of 30 vehicles, we find that in practice, those associations, these SACCOs, are very good at starting new routes. They take the initiative to go out and find new locations of service. And this is done by this kind of middle management cadre who invest money into it. They invest money, they write reports, they produce maps showing the routes they want to take, and they go out and they run tests. They even have these like little internal research bodies in some cases, and they will do corridor counts and check how many vehicles are already operating it and what the like predicted passenger volumes would be if they were to branch out to this new location. So, and we see the same thing in Jerusalem, just to go there a little bit, where it's this very, very great deal of geographic specificity by these small firms that really have a sense of ownership over different locations, and then also control the entry there, even though it's completely informal. So just to go back a little bit to the literature, some very, very fine-grained studies, not many, but a few, show how important this kind of localized geographic level of organization is at the root level, at the neighborhood level, and how much that's what's driving the expansion and ability of the network to actually respond to passenger needs, rather than assuming that it's the driver at the bottom of the food chain who's the sort of gutsy reactive agent. It's actually the middle manager who's able to see the slightly bigger picture and muster up the resources to support people and giving them that room they need to take a risk, subsidize their operations for those few weeks in order to actually be able to start up a new route. Yeah, so just to kind of summarize this a little bit, a lot of this operates right at the absolute boundary of profitability. There's no external subsidies. And it's really, really easy to kind of lose the vehicle, lose the job. And then, so everybody there has to be very, very careful. And we're seeing this kind of pattern in some places where vehicles are actually getting smaller and worse as competition gets more intense, rather than becoming better and bigger and more profitable, because everybody's just competing on these ever smaller margins of how little money I can buy this thing for, because I need to pay it off really, really fast because it will stop operating in 2 years. Yeah, and then from the driver's side, a lot of the searching behavior that we do hope to see, drawing a lot on Ndibati and Busin's work, who I think I saw here earlier, where even when there is this searching behavior, there's a kind of desperation and chaoticness to it, and it doesn't lead to consistent development of new routes in a way that actually support accessibility and support good mobility across cities. That's it. Thank you.
Perfect timing, Tamara. This is outstanding. So very, very interesting study. I have tons of questions, but I will open the floor. We have 3 minutes, but I will send you plenty of emails, because I was doing a similar study in Egypt, and maybe we can actually cross-refer. So we have a question here from Kara. You can read it off, Tamara. You can read it for Tamara, or I can read it for you. So. Do you think most of or all US transit agencies will be able to shift to subsidizing shared autonomous vehicles with shared rides across Uber, Lyft, and others?
I mean, I don't know. I think if trying to extrapolate this work onto the US scene and in integrating this idea of kind of flexible vehicles and demand responsive vehicles into a public transport system that has public funding, I think has potential, because what we're seeing also across studies of Uber that I've seen, which suffer from some of the same issues of labor relations, where drivers have a sort of conservative behavior, even as the algorithm tries to nudge them out of it. I think having a public subsidy for that is the game changer, where you're able to actually push the system to operate in ways that are useful for passengers, useful for equity, useful for providing kind of levels of urban connectivity that are necessary for a wider swath of the population than is currently working. So I really don't know. I know there's a few trials in different places, including in Israel, where there's this publicly subsidized TikTok, mm-hmm. And a few other efforts, but I'm really curious to see the data of that, and I'm not 100% sure it's available yet. And then haven't allowed jitneys in the US. Yeah. Well, the last jitney in San Francisco apparently stopped operating in 2006. And they do still operate in a few places, New York City, yeah.
Thank you.
Okay, any additional questions? So we have another question. This was a very interesting study, Tamara. In Pakistan, most of people, this is mainly a comment. Okay, comment again from Mike Hyland.
Yeah, I would
Okay,
guess
so I
they're like, it's a legal gray space in a lot of US cities. And it
okay,
depends
so
on also local regulation rather than sort of government, higher level federal.
Okay, I have one follow-up question to Kara's question related to the success of such model in developed countries, given the status of other competing alternatives. So my understanding of paratransit in the Egyptian context, that having a car or even active transportation is not providing like threatening competition to paratransit, because car is very expensive. Active infrastructure, like you can survive active infrastructure in Egypt. We don't have infrastructure, and also the special distribution or the special footprint of the city is so large to navigate through active transportation. So do you think that these models are limited to their context, or could be generalized into other contexts, namely North American context?
Paratransit. Well, I think I'm pushing back a little bit on whether paratransit's all that good at all. I think the current model, the way it operates in low-income cities without government subsidy, has a lot of gaps. It's great in the sense that it's providing really, really important mobility to people who have very, very few alternatives, including walk. Often the alternative is to walk, and we're talking in the context of the global north, we often think of walking and non-motorized transport as the good thing, the thing we're trying to shift people towards. But in the context of large developing cities, this is a health menace. This is wildly inequitable. It's exhausting. It's dangerous. So in this case, giving people alternatives, I think, is still very much on the policy agenda and what we should be doing. So these are really key services, but at the same time, they have like really, really severe limitations, including in terms of health, safety, labor exploitation, but also, as I'm trying to show, in terms of their ability to actually cover space. So I think here is where we see the inability of these fully atomized operators to effectively operate across space without some sort of higher level of organization, subsidy, and often regulatory nudging, which is actually making them more efficient and more useful. So I don't know what the US context relationship would be, maybe in the sense that the importance of how important it is to understand transit systems collectively as a single system rather than a given route or a given destination, and how important the profits and of operation there are in terms of the way they're pooled and subsidized. The most relevant case study is actually from the UK, where in '86, I want to say, Thatcher deregulated intercity bus routes. So then you saw a lot of this phenomena start to come in. A lot of these, like, supposedly was going to add all these actors and was going to improve the system. But in fact, they all started competing for just the same few corridors, often with smaller vehicles kind of raisin picking from the bigger vehicles. And then peripheral routes lost all service.
Okay.
So I would say, like, there's definitely things to learn about how transport systems operate, but I don't know if it's a model that I would be so enthusiastic to adopt.
Okay. Overall, I truly envy your PhD topic. And in hindsight, if I go back and redo my PhD, I will take this topic as my PhD topic. So this is great work. Thank you, Tamara.
Thank you.
Okay, so now we move into our third presentation by Gabe and Mike Hyland. So the Prescriptive model framework for regional transportation planning support. So Dr. Gabe is a postdoc research fellow at UC Irvine Institute of Transportation Studies. His work mainly focusing on developing artificial intelligence approaches for planning integrated mobility. Gabe also worked as transportation consultant with different level of public agencies. And just to see you the view of the BTRs, Gabe is actually interrupting his vacation and presenting live. I assume if he was connecting from his phone. If not, we have a backup for the video presentation, so we can actually play the video. And I noticed that we have Mike here to answer questions in the Q&A session.
Yeah, thanks. Yeah, thanks, Moataz. So far so good.
Okay, perfect.
Appreciate it. Yeah, let me just share my screen really quick. Awesome. Hi, today I'd like to talk about a reinforcement learning framework for strategic long-range urban transportation planning. This comes from my collaboration with Dr. Michael Hyland as a part of a research project funded by the National Science Foundation on revamping regional transportation modeling and planning. Okay. Our current urban transportation systems performances are at least partially the result of the historical planning. I'm here not to try to hold accountable the people whose decisions led to our current experiences in terms of urban sprawling, congestion, over-reliance on private autos, high emissions, inequity, aging infrastructure, and the staggering number of fatalities each year. Clearly, people have been discussing the lessons learned from these outcomes using their own mental models. But due to the complexity of the urban systems, it has been quite challenging to really correctly associate the decisions with their effects in a rigorous manner, especially considering these effects tend to have months, year, or even decade-long delays. In short, it seems lacking a systematic framework for learning the lessons learned, lessons in a more effective and confident manner so that we can make better decisions in the future about our transportation systems. The strategic planning of urban transportation systems is a critical endeavor for national, state, and regional development. In the United States, Regional Transportation Plan, or RTP, such as this one made by the Metropolitan Planning Organization, or MPO, of San Diego, California, is a part of a general plan that provides a long-term blueprint for the region. And that MPO usually takes multiple years of planning, data analysis, and community engagement to form a new RTP, which has a common vision for a region in terms of its future transportation systems, environment, housing and business conditions, economic development, and regional management strategies. RTPs usually have a 30 to 40-year planning horizon, and the regions must update the plan every 4 years or so, and usually with minor amendments during each planning interval, to receive state and federal funding for planned infrastructure projects. In addition to a long-term plan, the RTP also involves the identification of desirable near-term projects and policies through mainly the Regional Transportation Improvement Program, or RTIP, for which planning agencies hope they will receive funding from the state and federal government. We can further abstract the dynamics between a planning agency or quote-unquote agent and the corresponding region or quote-unquote the environment. The agent observes the state of the environment S at time T, as well as the associated performance or reward R, then make a decision A based on a certain policy pi for the next time step. The actions will influence the environment or the urban environment, which will render a new system state and reward. The goal of the agent, therefore, is to maximize the expected cumulative rewards with or without a discounting factor from the base year to the planning horizon year. The agent will then do this iteratively every few years. Since evaluating potential project and policies is too costly and disruptive to test in the real world, it is and it's definitely beyond the human brain capacity to really understand the impact of the complex intervention portfolios on urban dynamics. Planning agencies usually use a model-based approach. Some planning agencies go even one step further by systematically considering the interactions between transportation, infrastructure, travel activities, and land use conditions. And this joint model of travel and land use forecasting is commonly referred to as a land use transportation interaction, or LUTI model. This type of model is what we here refer to as the quote-unquote the environment in this conceptual framework. However, regardless whether we consider land use as endogenous, existing planning models tend to only evaluate rather than prescribe projects and policies. So we'd like to propose a sequential decision optimization method for prescribing rather than just evaluating planning decisions and their implementation timings in a region in which socioeconomic activities interact with the infrastructure and land use at different timescales. Now the question is how or what is the sequential decision optimization methods should be. Enumerating all possible actions and action sequences are clearly infeasible. Even a small system with just a few states and a few possible actions can take thousands or even millions of possible combinations. Dynamic programming also faces similar challenge of this quote-unquote curse of dimensionality due to the huge state action space. Control theory is more commonly used for stabilizing a system rather than minimizing or maximizing the objective function. It also does not really provide a general framework for finding the optimal decision policies for the highly nonlinear systems, especially outside the field of electrical and mechanical engineering. Simulation-based optimization using meta models or functions that does not provide rigorous prescription on how to evaluate and decide which scenario simulation to run next based on the previous simulation experiences. So we might have a redundant scenario runs, waste time and budget, which can be a bottleneck in our context, as the existing planning models usually take days to run, even using high computational resources. So reinforcement learning seems to provide a framework that can address all the concerns that we have above, especially in terms of the explicit consideration of the exploration trade-off and then the formal methods for dealing with the delayed rewards and penalties and their conditional applicability. This led us to choose to develop the framework based on the reinforcement learning, or RL. Under RL, or Q learning to be more specific, our problem becomes to find optimum policy pi that can maximize the value of the state action pair. The Q value here is defined as the expected cumulative rewards with a certain discounting factor from the present to the certain planning horizon. The Q learning provides theoretically sound, a practically feasible way to obtain Q value that quantify the quality of the decision action pair that considered both the immediate and delayed rewards. It is similar to the Bellman's equation in dynamic programming, but instead of working on the state space, it works on the state action joint space. So we can use this formulation to update Q recursively, and researchers have proven its unbiased convergence when the RL environment here can be described as a Markov decision process, or MDP, at least approximately. So if we can't, it's actually it's usually a good indicator that the boundary of our urban dynamics models or the RL environment model is too narrow for the planning decision context, and we should expand and incorporate more exogenous variables into the model as endogenous ones. As we allow state and actions to be continuous and discrete variable using a Q table that stores the stores the Q values of all the state action pairs is clearly infeasible. So we adopt this deep Q learning approach that approximates the lookup table, the lookup Q table using a deep neural network. Here we call it, so here we can use this Q hat to approximate the Q, and then the Q hat is approximated using a DQN or deep Q network. So you probably have guessed that the most eminent and probably the important term is the maximization term here, which represent the maximum possible Q value of the next system state by perturbating the corresponding action. So we here propose to use a Bayesian optimization approach to resolve this. Since maximizing the term, the Q value update formulation can be written as this, we can describe the function f that is essentially Q function, but with s fixed or the state fixed, or treating the s as the parameters. So the Bayesian optimization problem becomes just maximizing the f function. The Bayesian optimization involves two main steps. The first step is to use Gaussian process regression to construct a surrogate function of f based on the information we already collected from the objective function by evaluating the objective function. Then we construct an acquisition function, or AF, that achieve a balance between what we know about the objective function f and what we're uncertain about it. Then the next evaluation point is the maximum point on the acquisition function. By specifying this function, we can explicitly control or adjust the exploration trade-off. We here present the pseudocode and the conceptual flowchart of this deep Q learning Bayesian optimization joint approach. In short, we propose one, customizing the deep Q learning approach for maximizing the cumulative performance function across planning updates, multi-objective, and secondly, adopting Bayesian optimization at each planning interval to maximize the values of the state action pair, or Q values of the corresponding state of the urban systems. This section demonstrates the proposed framework using a simple example developed based on the county of San Diego in Southern California. The county is about 4,200 square mile region with around 3.3 million residents. We developed a low resolution long-term urban dynamics models based on system dynamics modeling paradigm to further simplify the model to make this recording possible that can fit into one screen. The model contains three main components: transportation infrastructure and travel activities, socioeconomic conditions, which mainly captures the households and employment dynamics, and their third component is land use that captures the conserved transition among residential, business, and vacant land. The three and here is the three sliders represents the three decision variables, and we select five. The three decision variable here is represented using the sliders, and then we have this 5 state variables that we selected to represent the system state. But of course, the goal here is to build this intelligent agent to help us figure out the optimal policies and projects and their sequences and timings. So another reason we choose this model is because it's particularly good in terms of neatly capturing the delayed effects and situations where a good policy can make system to get worse before it get better, and a bad policy can make a system seemingly improve in the short term but worsen the system in the long term, which is unfortunately but a pretty common reality. So we tailor the model to match this basic needs of the regional planning to facilitate our demonstration of the RL algorithm instead of the RL environment.
Gabby, if we can wrap it up, we have 1 minute left.
Oh, okay. So we have this. We tested the RL algorithms, and with different hyperparameters, defined the reward function, and we got a pretty. Seems we got some pretty promising results, and we also examined the individual instances and noticed the improvement of the coordination among different control variables. So the future steps, we have we propose these RL algorithms using the DQL Bayesian optimization joint approach, and we identify 3 main future research directions, and appreciate your attention. Thank you.
Okay, perfect. It's 1 p.m. EST sharp, so this means that we are on time. So I will open the floor. We have 3.5 minutes for Q&A. So if you have any questions.
Jason, any questions about Bayesian estimation, or Jacob, Ollie, Thayanne? I haven't seen that term before, Gabe, so it's nice to see you here.
Oh, the Bayesian optimization.
Michael, nice job. Michael's co-author.
Yeah, and yeah, I appreciate Mike's help as well. Thanks.
Are you guys enjoying reinforcement learning? Is that helping with a lot of previously crazy complex problems?
Go ahead, Gabe.
Oh, I mean, like, yeah, it was just and it's very interesting, kind of a new emerging field, and since it's matched well with this particular decision context, and we a lot to learn, a lot to test, and a lot to explore. So it's a pretty interesting domain. Thanks.
Yeah, basically, I wrote the proposal and it got funded, and then I hired Gabe to actually figure out how to do it. But the main idea actually behind the work is that the way planning is done now, right, is we have these very intense, complex, I'd say behaviorally sound models in which planning agencies kind of just run a bunch of combinations of policies and infrastructure investments through those that they think, based on a lot of work and a lot of analysis, will be good for the region. But we have this thing called optimization that I think we should try to use to identify good combinations of policies and projects in the region. But of course, these regions are complex and the decision space is enormous. So we're trying to figure out the mathematical tools that can help us do it.
Yeah, I'll put something in the chat box that a postdoc of mine was recently trying for optimization of fares and fleet sizes. And the fares had a couple different pricing variables for shared autonomous vehicle fleets across a region. So that's a very complex objective function too.
That sounds great. Thank you.
Thanks.
Okay, perfect. I'm back. Sorry, I lost my internet. I don't know why. So we still have one more minute. Sorry, if we have any. Okay. So thanks again, Gabby. I'm sorry for interrupting your trip. Very interesting presentation.
Yeah,
okay.
I'm glad my Wi-Fi works and I appreciate your.
Perfect. Your Wi-Fi worked better than mine, so.
Oh,
yeah.
Thanks.
Okay, so let's move on to our fourth presentation today: multi-regional analysis of combined near-term smart mobility scenarios using Polaris. So the presenting author today is Dr. Joshua, is the principal computational transportation engineer and manager of the transportation system and mobility group in the vehicle and mobility simulations section at Aragon National Lab. He's an expert in agent-based modeling, behavioral analysis, transportation simulation, travel data, led more than 50 peer-reviewed journal articles, book chapters, editorial, and currently a member of the TRB Transportation Demand Forecasting and Traffic Simulation. Dr. Joshua earned his PhD degree from University of Illinois at Chicago in 2011, and research focused mainly on travel behavior decision-making from both modeling and data collection perspective, and the impact of connectivity, automation, and control on travel demand and transportation. So without further ado, the floor is yours. Again, if I turn on my screen, it means that you have 2 minutes left, okay?
Excellent. Thank you for the introduction. I will be presenting today a multi-regional analysis of combined near-term smart mobility scenarios using our Polaris modeling workflow. This is a large-scale research program that was done for our Department of Energy Smart Mobility consortium that myself and a number of colleagues listed here, as well as many partner labs and universities engaged in to run these large-scale scenarios. So just a bit about the motivation behind this work. As an energy lab, we know that there are fairly aggressive decarbonization goals that have been proposed, to address the very real challenges of climate change, energy security, and others. And we identify that a holistic approach is needed to achieve these goals, to really understand how technologies or solutions or strategies in one sector of the economy, urban organization, regional structure, transportation, and so on affect each other. So we know that changes in vehicle electrification or vehicle charging, for example, have impacts. They have needs that need to be understood. What the metrics from vehicle deployment would be, but these also have follow-on effects and impacts in other areas of the economy, things like land use or traveler behavior. You know, the need to charge a vehicle can change how I travel during the day and so on. So any technology we look at, any decarbonization strategy across many sectors of the economy that we look at have these complicated interactive effects with other technologies and other sectors. So it was identified that we need to develop a multi-level, multi-fidelity modeling framework which can generate many of the metrics of interest, things like energy and emissions directly, but also looking at greenhouse gas, economic impacts, equity impacts, mobility impacts, and others that are important to our sponsors and our stakeholders. To address the complexity of this problem, we have engaged in a multi-year research program, again, across the lab complex and with many university and other industry partners, to develop such a flexible workflow that enables us to engage in this multidisciplinary collaboration and have end-to-end modeling workflows to run upstream from long-term changes in land use and vehicle markets all the way down to how individual vehicles travel and movements change. This workflow to connect various tools and consume many different data generated from different data sources into this end-to-end workflow to generate the metrics that are necessary. So this is a combination of many tools, everything from mesoscopic simulation and regional travel demand simulation, freight and goods movement, microscopic movement of vehicles, multi-vehicle control, so even the level of communication with infrastructure and between vehicles, and all the way down to individual powertrain energy consumption to generate these metrics that we can use to evaluate different decarbonization pathways. So we have, in the process of putting this workflow together, also engaged in any number of individual studies about how different potential smart mobility, future mobility, or connected mobility technologies would impact regional mobility. So we have explored different scenarios around congestion pricing, for example, with a lot of studies we have run in the Austin, Texas region, looking at different potential strategies for that. Looking at vehicle connectivity, vehicle to infrastructure connectivity through the use of connected vehicles communicating to roadside equipment units, exploration of automated vehicle technologies from partial automated highway driving to others, looking at impacts of that those technologies could have on highway throughput, as well as potential changes in traveler behavior, and an exploration of freight policies, so shifting to off-hours delivery for certain goods movements. So these were all identified as high priority areas of interest for various stakeholders we looked at, that we engaged in different studies. And for this round of work, we decided to explore how these technologies interact both within region and across different regions. So we want to look at a multi-region objective. So the study here is really to look at these scenarios that were identified with our stakeholders with a core focus in the current year on more near-term implementable technologies. So things that we expect to come in the next 10 years or so, at least to some extent. And again, that's V2I communications, road pricing, partial vehicle automation, and freight delivery policies, and run this across a set of cities that we have been modeling internally, including the Atlanta, Austin, Chicago, and Detroit larger metro areas, to evaluate, look at these impacts, look at how these different technologies interact, and then make comparisons and inferences across regions. So with the goal here, we want to understand these differential impacts and see how changes and different local contexts, so things like the transportation infrastructure available, behavioral patterns, land use organization, demographics, and so on, how these can lead to different findings across regions. And finally, as we're looking at decarbonization, we want to understand the impact of advanced vehicle powertrain technologies where they are not explicitly a part of the scenario setting itself. So in terms of scenario design, we did have these 4 scenario levers, the CACC or partial highway automation, road pricing, off-hours delivery, and then roadside unit connectivity. I will present in this study, however, we are limiting it to the 8 scenarios per city where the roadside units were turned off. And this is actually a finding we had when running through our model, is that without, so the roadside unit to vehicle connectivity was studied in the context of mitigating non-recurrent congestion, so incident response. We find it didn't have much impact when we're running these average day models, which we typically do with the travel demand simulation for these cities, just due to the performance of a dynamic traffic assignment. So being at an equilibrated state meant that the vehicle to infrastructure communication, passing traffic state information to allow dynamic rerouting didn't have any impact. So that those results are basically elided from these results, but those scenarios were run. For the study areas we looked at, so I mentioned we have our 4 larger MPO regions, and then the Atlanta area also ended up being a multi-region model itself, where we also connected to the Chattanooga and Knoxville metro areas to look at some more inter-regional travel as well. So we ended up with a model area, if we combine all 4 of the regions, into about let's say 24 million people in a model area of over 100,000 square kilometers. So we say this is the geographic size of South Korea with the population of Australia. So it's a quite extensive geographically and in terms of population scale models that we are running here. So just in terms of results, again, it's a lot of runs. It's thousands of simulation runs. So a lot goes into pulling this together. Just some high-level aggregate results. So if we look at the impact on total travel, so in terms of vehicle miles travel across the 4 regions for the 8 core scenarios here, we can see the variable nature of the impact in different regions that these different bundles of technology would have. So one immediate finding is that the Chicago region has a lot more sensitivity to pricing scenarios, really due to, there's a couple of factors we have identified. The primary one here is the existence of more advanced modal alternatives. So Chicago with more a highly developed transit network gives opportunity to respond to pricing by doing mode switching to a much greater extent than some of the other regions. We also see that Chicago and Detroit to some extent have more latent demand, which is unlocked by the deployment of the CACC vehicles. So if we look at 4 and 5, the scenarios where we have deployment of the partial automated driving vehicles with a reduction in travel time value, we see a greater increase to an extent in those regions than we do in Austin or Atlanta for a variety of reasons. One, with these vehicles only operating in highway conditions, the Austin area has more limited highway alternatives, so there's a more limited area where these vehicles would be effective. In the Atlanta region, the organizational structure of the sort of funnel type transportation network limits the ability of these vehicles or of the system to respond to increased congestion. So if we look at the speed change, or alternatively, if we look at the hours traveled, we do see congestion increasing in Atlanta, even though people aren't traveling further, just due to the way that the network itself is structured. When we focus on the congestion pricing, so the delay-based pricing, since we are directly charging delay or congestion, we do see speed increases, right? So we're making hours traveled more costly to consume, so people consume less of that. Especially in Chicago, again, where there are modal alternatives, we see 11% increase in network speeds under the congestion pricing scenario. So it's a fairly impactful policy in terms of getting improving mobility in the region. Where as we look at CACC deployment, it has a more mixed impact. So again, it does cause additional travel in several of the regions, including Chicago and Detroit. However, because due to the connected nature of the limited vehicle automation, where the vehicles can communicate, the V2V communications, it does increase the highway throughput to some extent. So even though we are generating more travel, in some instances, the speed is either staying the same or increasing slightly. So there's some offsetting of the downsides and upsides of that technology from a mobility perspective. Finally, if we wrap this together with our energy forecast, we can see that travel efficiency is mostly increasing across these bundles of technologies. One key finding here is that they are generally not additive. So they interact, the technologies, whether it's off-hours delivery shifts, the CACC deployment or the road pricing, interact in complex ways. So you wouldn't say, we see a 3.7% increase in travel efficiency due to congestion pricing, and a 1.7% due to off-hour shifts. So if we had both of those, then we'd see 5.4%. So there is some complex interaction between these technologies that in many cases limits the overall benefits when they are combined. One other note to focus on here is that we are only seeing about a 5% increase, but it's important to note this is all autofocus. So when we layer in the vehicle technology improvements or increased electrification, we could see potentially much greater impacts in travel efficiency. Due to timing, so this is just another way to look at the impacts. This is the marginal impacts of different technologies, but I'll go ahead and skip forward. So I see Moataz's screen is on. One new addition that we are doing with a lot of this analysis is looking at equity environmental justice metrics. So if we compare the impacts on cost burden by income quintiles in the different regions, we can see how these technologies differ in terms of their impacts in different and different income quintiles, where the congestion pricing scenario tends to have a more equitable distribution, where some of the greatest benefits accrue to the lower income quintiles. We can also look at this in terms of emissions. So we see the differing in the baseline emissions on the left for each side for each city, where some are more equitably distributed than others. So Atlanta has a reverse equitable distribution, whereas Chicago is more generally equitable. And then we can see what impact different technologies have, where the CACC deployment tends to have most impact on lowest and highest, just due to where the highways are organized in Chicago. It's different for other regions. So again, in conclusion, we did find that road pricing has the largest impact in all the cities we studied, although it varies by city fairly substantially. CACC had small and mixed impacts just due to how it was assumed to impact drivers and vehicles, where we did see average speed increases for Austin and Detroit, but reductions for Atlanta, so some significant regional variation there. Off-hours delivery led to mostly consistent speed increases across all scenarios, although the effect was fairly low, just due to the 5% shift. And we observed land use and transportation systems displaying complex interactions depending on where activities are located, how they are served through the regional transportation network organization, and then what modes are there to serve those trips, with the cities with limited modal options having some reduced sensitivity to pricing signals. Some next steps that this work has motivated: we do want to continue to explore the integration of average day and non-recurrent technology. So again, things that are more focused on responding to incidents like roadside units. How do we start incorporating that into our average day models? We need some theoretical work on that. We want to look at what additional technologies to layer into these studies as we expand our scenario analysis to 100, 200, 300 different scenarios by city. How do we look at EV charging, connectivity, others? And these, again, are always driven by our interactions with stakeholders on the individual MPO level, as well as larger groups and organizations and other agencies, models that we can link into our workflow. One of the key things we want to focus on is expand our pricing scenarios. So do we look at pricing different mode alternatives, as well as if we are doing congestion pricing type solutions, what do we do with the revenue that's generated there? So in current simulations, it's just kind of run into the ether, but can we use those to show additional benefit of congestion pricing through reinvestment in transits or other modal alternatives? And then how do we layer different vehicle technologies and fleet assumptions into these scenarios? So I think probably about out of time, so I'll stop there, but thank you to all for listening. And if there are further questions, I can either answer now or be contacted through email shown here. Thank you.
Okay, perfect timing, Josh. Amazing. We are exactly 1:20 or at 12:20 CDT. So we have a question here from Kara in the chat box, and I think it's answered, but I believe for the benefit of the audience, maybe if you would like to add more comment on the question. It's about the missing 60% of the centerline miles in Chicago, and also I think Austin is missing about 45% of the roadways. Can missing network lead to optimistic results in these agents? So if you would like to comment on this.
I'm assuming, Kara, this is referring to local streets and cul-de-sacs and suburban type streets that are typically missing from these models. It does. It is fairly significant portion of centerline miles, although much less if you look on a VMT basis. So typically it's less than 10%. We are exploring and possibly you're aware we're working it with some of your team and other teams as well. What impact that has, especially those missing lane miles on shared vehicle type systems. So if we have vehicles running through and picking up people and doing door-to-door service, it becomes more important both on the shared mobility side as well as on the local delivery side, as we do have substantial freight simulation, where moving a couple blocks to drop off and then the Amazon truck moves to the next few blocks. So having all those centerline miles missed does introduce some bias along those lines. So we are currently exploring what it looks like if we have that and don't have that, where we make those assumptions, what that impact looks like. So yes, it's a substantial problem and substantially complicates the simulation if we try to have all of these centerline miles, but it's something we're actively exploring.
Okay, perfect. So any additional questions? I don't see any messages. So thanks again, Josh, for very interesting presentation and sticking to the time. I know it's the hardest job ever is to manage time during presentation, especially all the topics are very interesting. So I think now we will move into our fifth presentation of the day with Emma. So welcome aboard, including public microtransit and choice models to understand use before and during the COVID-19 pandemic. So Emma is a PhD candidate in transportation engineering at UC Berkeley, and her dissertation focuses on the equity, disability, and environmental impact of public microtransit services. Emma received the NSF Graduate Research Scholarship and 3 Federal Highway Administration Dwight Eisenhower Fellowships. Wow. Emma has worked in Evolve National Transportation Systems Center, the Minnesota Department of Transportation, and Twin City Metro project. So the floor is yours. Quite excited to see your presentation.
Great, thank you so much. Yeah, so my dissertation focuses on partnerships between public transportation agencies and the private sector to integrate on-demand microtransit services with traditional fixed-route public transit. And so I'm particularly interested in the equity and accessibility and environmental impacts of public microtransit and how these impacts have changed during the COVID-19 pandemic. So how are we defining public microtransit? Let's see. My slide will respond. There we go. So we're defining public microtransit as on-demand services run by or for public transportation agencies. And these use smartphone apps and ride matching and routing algorithms. And we're looking at van-based services. So even before the pandemic, we had tried to track down, all these services that we could find, and there were 62 different pilots that we located across the country. And this map actually does include like partnerships with Uber and Lyft, subsidies for those types of services. But we really honed in on the light blue that you see in this map, which are what we called agency run services. So it's like using those van-sized vehicles, and the private partner provides the ride matching and routing algorithm and the app. So obviously, the pandemic caused a big hit to fixed route public transit ridership. And we have not fully recovered from that. And these van-based on-demand services have sort of come in during the pandemic and said, for your remaining riders or for those early days of COVID, for your essential workers who are transit dependent, like our services can provide a good alternative. And they've even more bold, they've presented themselves in some cases as like a superior alternative to fixed route transit. And when we were tracking responses by public transit agencies early in the pandemic, while fixed route services, some fixed routes were shut down altogether, or service was decreased. These public microtransit services actually did increase, and agencies started offering new services. So as these services become more common, we want to, analyze them and figure out what are the actual VMT accessibility and equity impacts of these services, and how can agencies design these services to optimize these impacts in different both pandemic scenarios and then also thinking ahead post-pandemic. So the way that we decided to look at these questions is first we surveyed people in the service areas of 14 of these agencies that had a microtransit service, both microtransit riders and also people who had not used the service. And then we will apply that model to the microtransit trip data from 8 of those agencies to estimate replaced modes and calculate impacts based on that. And then also adjust variables in the model, service design variables and also COVID conditions to see how those changes might impact mode share and impacts of these services. So first I'll talk about the mode choice model and the survey. So from April to December 2021, we surveyed just over 1,800 people across 14 of these public transit agencies that offered a microtransit service. So about 2/3 of those were people who had used the service more than twice, and then about 300 who had used it once or twice, and then 300 who hadn't used it at all. And each person answered up to 6, 3 pre-pandemic scenarios and then 3 scenarios set during the pandemic. And this is just an example of what was seen in the survey. So this would be an example of a pandemic scenario. So we described what state of spread COVID was in, vaccine availability, whether the respondent themselves and their family had been offered the vaccine, and then the context of the trip, and then typical cost and time characteristics, as well as reliability. So we were interested in including this because we had heard from a lot of the public agencies that this was a particular challenge. You're given, just like in Uber and Lyft, you're given a estimated arrival time, but these services often had delays past that time, even up to this level of 15 or even 30 minutes late. And then we also talked about the number of other riders on the vehicle and the number of transfers. And we looked at 7 modes, so including the public microtransit mode. There was also a ride alone, Uber, Lyft, shared ride, Uber, Lyft. We had drive alone in a personal vehicle for respondents who had reported having access to a personal vehicle. We had fixed route bus. We also had 2 first mile, last mile modes. So both this public microtransit as an access mode to fixed route bus, and also an Uber and Lyft as an access mode to fixed route bus, because in a few instances, agencies do restrict use of their public microtransit as a first mile, last mile option. You have to be starting or ending your trip at a transit station. But since that would be a lot to see in any given scenario, it was randomized. In a specific scenario, respondents would see 3 modes. So from this data, we estimated a mixed logit mode choice model, compares preferences before and during the pandemic, and then it also includes shared air components to start to see how is microtransit correlated with these other modes that I just described that we had in the model. And I'll be talking more about that piece in actually the flash session 1. But right now I'll focus more on the other parts of the model. So let's see. So this slide, it's a lot, but I'll just highlight a few of the more interesting findings. And so in the red box there, you can see that the negative impact of trip cost was actually less negative for the COVID scenarios. And the way that we thought about this is that potentially people are worrying less about cost and more about their safety on the mode during COVID. We also found that as local COVID case counts increase, people are less likely to choose the Uber and Lyft modes, even less likely to choose the public microtransit mode, and even least likely to choose the 3 modes that involve a fixed route bus. And that tracks with you know, what you might think when people are trying to avoid, you know, more people on the vehicle. We also found that agencies that offered weekend microtransit service in addition to weekday service, there was a boost in likelihood of choosing that microtransit option. We found that respondents preferred microtransit over fixed route bus on trips that were to or from a healthcare appointment. And also from a store. So you can imagine, you know, coming out of a grocery store with bags or purchases. So respondents did, you know, drive alone was perceived as most convenient, but then the microtransit and the Uber and Lyft modes were next most, and then the bus modes were least favored for those trips. Another interesting thing, age, so older individuals are less likely to use shared modes, especially during the pandemic, which makes sense. This was the shared modes that were most impacted were the shared Uber, Lyft, and then the 3 bus modes. And then ride alone Uber, that negative impact is a little bit less with age. So they're a little more likely to do the ride alone Uber than those other modes I just mentioned, but microtransit actually didn't come in or didn't show up as being less negative or less preferred as compared to drive alone as age increases. And so one way that we're thinking about this is that several of these services sort of approximate, you know, paratransit services that had existed before. And a lot of those paratransit services do serve an older population. And so there might be a clientele, you know, carryover to these public microtransit services. And then another equity-related finding was that for respondents who reported not owning a smartphone, they are more likely to use the 3 bus modes. And so that we did see, you know, a barrier to using the on-demand modes and the drive alone modes for those individuals. Some, you know, initial implications from these results. Just, you know, just like I had said at the beginning of the talk, that agencies started, you know, introducing new microtransit services as COVID hit, and even as they were reducing their fixed route services. And that it seems like from our results that strategy may make sense in terms of trying to retain riders, because that negative impact, because riders preferred microtransit as case counts increased. And then also, you know, maybe when agencies are thinking about where to provide this public microtransit service, it seems like maybe healthcare facilities and shopping centers might be a target. Also, agencies, you know, can target the service to riders of all ages, especially lower income individuals with less access to personal vehicles. Those were the demographic groups more likely to use microtransit. And then the smartphone access does remain a barrier. And some agencies, actually all agencies that I know of do offer a call center option. So people without smartphones can call into a central line who will then organize the trip for them. But that clearly, you know, isn't as easy as booking it yourself. So just exploring additional ways around that barrier. I have seen, you know, one agency that has tested out provision of a smartphone, so that could be something to look at. So the next steps for us are to apply the model to public microtransit trip data. We have trip data from 8 agencies. That's over 400,000 trips over 1.5 years, starting just before COVID hit. And start to look at what the replaced modes might be based on our model and calculate the impacts from that. And then also, you know, adjust the model variables around service design and COVID conditions to see what the mode split and impacts might be from changes there. And this is just an example. So when we apply the model to that trip data, you know, as microtransit wait time increases and cost increases, you see the mode share go down, which makes sense. Here you see a high microtransit mode share, ranging from 20% to 30%. And something to keep in mind is that this is applied to trip data that were originally all microtransit trips, and also most of the respondents. And this is also assuming that the people making the trips are frequent microtransit riders. So we can test this again with assuming that the people have never used microtransit, and also adjusting the model constants to match a more realistic mode share. So like I said, next steps is to do this type of analysis and analyze changing mode splits with different service conditions, like availability of weekend service, as with changing COVID case counts. And then also, you can also measure this mode split change, how it differs by income group, age, vehicle, and smartphone access. So I'll leave it there. Thank you so much.
Okay, perfect. Thanks a lot, Emma, for the presentation. So I will open the for questions. So I have a couple of questions. So one of them is related to reliability of the service, and you tied reliability of the service to delay function. So the bus is coming, how often the bus is coming on time. Based on, we did similar study, but for traditional transit service. And the biggest issue when we actually distributed our pilot survey was early arrival of buses. And we did the same for a microtransit service in Hamilton City in Ontario. And also early arrival of buses was a dominant issue, that people can tolerate late arrival, but they will never accept early arrival. So the bus will come a minute earlier than a schedule, and people will actually miss the bus. So if you can provide some comment on this and how this might impact your study.
Yeah, for us, for these microtransit services, late arrival for the public microtransit services, late arrival was definitely always a bigger problem. And if they did arrive early, they did wait. In conversation with agencies, that tends to be what happens. Is if the vehicle does arrive early, they would wait. And because it's app-based, they're able to send an alert. In some cases, some agencies, it depends on how sophisticated their app is, but they could, alert riders of an earlier arrival time, or people can track it in their app and see that their vehicle is arriving early, and in some cases arriving late. So that issue, it's interesting because we didn't test that. So we didn't test their response to an early arrival, but just in conversations with agencies, and since we were already testing such a wide range of trip characteristics, we had to pick and choose, and agencies were most concerned about what would be the impacts of if they were able to get that delay under control. But yeah, there are in cases, delays of up to like 45 minutes or more. So that's definitely more of the challenge here. But
okay, my question is related to what kind of the associated health measure when you say during the pandemic. So during in Canada, at least, we had like severely different health measures related to physical distance, wearing masks, and number of like reduced occupancy on the vehicle. So I was wondering if you can comment on the variation between this is the norm, and this is like or pre-COVID versus during COVID. So it's like mask mandatory, physical distance mandatory, like all these were actually in effect during your experiment, or?
Yeah. So we debated, including that as a variable in the scenarios, but like I said, we just had so many already. So we did put in language in the survey before they saw any scenarios to assume that those measures were in effect during the COVID scenarios. Okay. So we didn't explore the impacts of changes in those policies. Yeah.
Okay, perfect. Thanks again. I'm a very interesting topic and presentation.
Thank you.
Okay, so now we go into our final presentation of this session. So review of resilience hubs and associated transportation needs by Thayanne. She's an MS student at University of Alberta and a member of Resilient Sustainable Mobility Evacuation Group. And during her master's degree, she will be researching evacuations here in disasters resilience hub. And she works under the supervision of Dr. Stephen Wong, received bachelor degree from civil engineering in Federal University of Alagoas. Hopefully I'll pronounce this in the correct way, in Brazil. So the floor is yours, and we have 15 minutes, and whatever time left you will have for Q&A session.
Can you see my screen?
Yep, perfect.
Okay, thank you. Hello everyone, I am Thayanne, and today I'm going to talk about resilience hubs, the conceptual framework, and transportation needs. This presentation will cover the context, the conceptual framework, the transportation needs, and the conclusions. Many cities have been facing larger and more frequent extreme weather events due to unprecedented change in the global climate. So consequently, many aspects of society, such as governments, infrastructures, and transportation, have been directly affected by ongoing hazards, disasters, and rapid urban growth. We also observe that the impacts of climate change and non-climate related disasters are becoming more severe and costly. And we also noted that their effects differ depending on the local context. And moreover, the way that people understand these extreme weather events can be explained by their own experience and their perceptions about the climate change. But who are the most vulnerable people to these disasters? The literature points that the people living in informal settlements and those already marginalized are the most vulnerable to disasters. And the number of people residing in these areas has increased due to the rapid urban growth, and that is usually unplanned. And according to the United Nations, in 2018, more than half of the world's population were living in these urban areas, and by 2050, it's estimated to increase to 68%. Thus, these communities need new ideas and tools to ensure that their residents both survive and thrive. And many studies have been showing several crucial requirements for governments that continue to arise in most disasters, including evacuating people safely from risk, finding and operating sufficient and livable shelters, connecting resources with survivors. And it's important to mention that these needs in disasters are often facilitated by transportation infrastructure and response strategies, and that the current evacuation shelters only work during disasters and are often seen as uncomfortable and under-resourced. Then there is a need for a hub that can holistically address the challenge during disasters and build the community resilience during everyday conditions. In this context, one potential idea is to develop resiliency hubs. Before I present the resilience hubs concept and characteristics, I will talk about some preceding hubs. I will start with evacuation shelters, which are usually public shelters where anyone may seek safety during an emergency. And depending on the type of disasters, these evacuation shelters can be planned for an open area, for example, parks or squares, or an indoor place, such as libraries, recreation centers, and government buildings. These indoor locations are most common because their structures can protect people from multiple hazard risks. And based on the period of time that people need to stay in these shelters from the commencement of the disaster, the evacuation shelter can be categorized as emergency sheltering, a temporary housing, or permanent housing. Although they are an important tool during disasters, the literature indicates that they are not widely used. Only 2 to 11% of the evacuees go to public shelters. And these shelters have some limitations. For example, for access, they are considered uncomfortable, unsafe, and lack a necessary resource. People usually complain about they are crowded as well, so it's make disturbance and noise, and is excessively crowded. Second kind of hub that preceded the resilience hubs are the community hubs. They are multi-purpose institutions that aim to help the well-being of the community. So they are generally designed to meet the needs of the community through local service and resource. For example, they have education activities, health service, or recreation activities. And they also have some limitations like the evacuation shelters. For example, the poor land use planning may result in an appropriate placement of the community hub regarding the accessibility and vulnerability. They are also usually unprepared to support the community during an emergency. A third example of preceding hub is the mobility hub. They are places where passengers can transfer between a variety of roads and transportation modes. And they are an opportunity to integrate various sustainable transportation modes and increase the city's connectivity. They can now encompass some amenities which support the passengers and turn them into multi-use space, transforming them from a place to destination from a place of transfer to destination. And some of the amenities that they can include is washrooms, Wi-Fi, food courts, or gyms or banks. And however they have these amenities, they are not structured to serve as a shelter during a disaster. And in many places, especially in North America, there is a minimal attention to building the mobility hubs. After reviewing these three preceding concepts, we found some key problems. For example, mobility hubs and community hubs have been largely insufficient to work during disasters, and the evacuation shelters not only work in disasters, but they miss the accessibility and mobility, the accessibility of the mobility hubs and the everyday benefits of the community hubs. The strategy to solve this problem is to better collocate resources and enable functionality to solve these problems. The strategy to solve this is to better collocate resources and enable functionality during disasters and everyday conditions, because this can help the community to improve climate change and can increase the community resilience for climate and non-climate emergencies. So the resilience hubs are a good fit to help the communities in this context. The resilience hubs were first comprehensively described by Baha in the report Resilience Hubs, Shifting Power to Communities and Increase Community Capacity that was prepared for USTN. They are defined as a community service, the building and its surrounding infrastructure, and they are created to support the residents, coordinate communication and service, and provide the resource distribution before, during, and after disaster. They aim some physical, ecological, and social key goals, such as improve quality of life, provide social service, improve equity, improve community resilience, reduce greenhouse gas emissions, and provide more efficient emergency management and climate change mitigation. Although all this functionality, they can operate in different modes to achieve these goals. They work in everyday or normal mode during the majority of the year. They shift to response or disruption mode when a disaster happens, and they operate in recovery mode in a post-disruption scenario. So for each of these operation modes, they may have different service to provide. For example, during normal day, they can offer food bank, health service, or childcare. And during disasters, they can offer medical supplies, food, or a shelter. Until now, we saw the resilience hubs concept, the key goals, and the operation modes. But where these hubs are going to be implemented? The literature suggests that selecting existing well-known and well-utilized places to be retrofitted into resilience hubs. They should be large enough to ensure daily program needs and to be able to provide response and recovery activities in the event of disruption. They should also be located in an area that can be accessed by a large number of residents on foot and close to evacuation route or major road. And they also should be integrated with facilities that do not need significant investment and upgrades. Moreover, they may be designed in a way that make it an attractive place, even in a no-emergency scenario, combine the disaster features with the everyday amenities at the community building. They can also go beyond major disasters. For example, they can be used as a cooling center or a warming center. They can be in a cleaner center or a training center for disasters preparedness. And they have many benefits, but there is some limitations that we found in the literature review. And most of the limitations are related to transportation. For example, transportation has not been fully considered in the placement of a hub or during its designing or planning phase. There is no evidence on how relief supplies will reach hubs during an emergency. And mobility equity has not been part of resilience hubs. Another important limitation is that there is no metric or key performance indicators for evaluation. Now let's go further in the transportation needs. The existing literature pointed to transportation aspects that should be considered in the implementation of resilience hubs. First, they should be in an area that can be accessed by residents on foot. And second, they should be close to an evacuation route or a major road. However, there is no evidence on how these elements have been considered in the design and implementation of current resilience hubs. In addition, they do not encompass the complexity of evacuations and do not consider the transportation resource needed for vulnerable populations. Another limitation is that there is little guidance on how to better plan resilience hubs. And it's also important to understand how the resources reach the hubs during the disasters. So the resilience hub plan should contain information on how, during a disaster situation, the resource will reach the hub and who will provide them. Another strategy that can improve relief chains is to preposition the resource in hubs or other key locations. And to ensure that resource will reach the hubs, they should be part of the city's evacuation plan. So the city should have a well-defined evacuation plan, and residents should have knowledge of this plan. Moreover, the evacuation strategy should encompass the transportation modes used by the residents to go to these resilience hubs. Therefore, the resilience hubs should be part of the evacuation plan and ensure the mobility equity. We understand that the placement of multiple modes can allow evacuees, especially the vulnerable population, the ability to reach resources more quickly. In disaster situations, the vulnerable population include but are not limited to carless, low income, older adults, or children, and individuals with disability. So we can think about some transportation strategies that can be implemented to improve the mobility equity. For example, the Resilience Hub may implement a multimodal system that prioritizes public transit, or integrate shared mobility for point-to-point transportation, or ensure accessible and reliable transportation to individuals with disability. It's also important that the public transit employees are trained to act during an evacuation. So the drivers must be prepared to serve all evacuees during an evacuation situation. They also should be trained to serve to all evacuees without discrimination. And they should also be prepared to assist older adults and individuals with disabilities. The conclusions of our studies until now is that resilience hubs have a promised future. They can help the community increase their resilience to climate change and build social cohesion and preparedness for a variety of emergencies. The existing literature has some guidance on how to plan hubs, but more studies are needed to improve the hubs designing and implementation. Also, studies are needed to better evaluate their effectiveness during everyday conditions and during disasters. And although the transportation is a key element for resilience hubs, it has not been sufficiently studied or considered in the resilience hubs planning and implementation. The next steps of our study is to survey residents of the city of Edmonton and conduct focus groups with vulnerable population. Then we are going to analyze the data to understand residents' needs in evacuation and for resilience hubs, and provide the recommendations to guide city plans for evacuations and resilience hubs. I'd like to thank my co-authors and supervisors, Dr. Stephen Wong and Karina Bossioni, and our funders, the City of Edmonton and Alberta EcoTrust. Thank you.
Okay, perfect timing. I must give it to our presenters today. This was amazing timekeeping exercise. So Thayanne, thanks for great presentation. And now we have 2 minutes for Q&A, 2 to 3 minutes, because the same URL will be used for the next session. So if you have any questions, and just remember, I think Jason sent an email with all like the contact information for the authors. So if you have additional questions that you would like to ask one-on-one, just feel free to email the presenting author or any of the authors like on each of the 6 studies that we have discussed today. Okay, so I don't see any questions, and I received just another warning that we need to shift gears into the next session. So again, thanks a lot, Thayanne, for outstanding presentation, and best of luck in your research. And I would like to extend the thanks to all the attendees and the audience today. Very important session, and thrilled to be again part of the BTR for the 4th year. So this is amazing, and hopefully I'll see most of you around in the next session and also for tomorrow. So that's it for me. Just a gentle reminder that we have 2 parallel sessions happening starting from like 1 until 3. One is related to transportation safety, and the second one is electrified transportation. So these are 2 parallel sessions, which will be followed up by flash sessions starting from 3 to 5 CDT. Okay, thanks again, and have a good one.